Hey class, I hope you had a great weekend. We have a bit of I think it's a bad news, good news situation. So, um, bad news, there's an exam today, beginning today. You'll have a week to complete it. Uh, More bad news, we haven't properly done a review on this, and then the last bit is that we haven't done homework assignments on it either, as far as I can tell. But the good news is that the next two lectures will cover exactly what you need for the exam. So we'll look over the problems, we'll discuss them briefly, and I hope this motivates you to pay attention to these lectures as we go along. I've increased the font size on the code and the text whenever we review the exam. Um, Happy hunting. All right, let's go. Okay, so there's two problems. There's the graphs problem and the trees problem, and then there's an extra credit problem. So for this one, you need to use Dijkstra's algorithm to find the shortest path. Now, if you're or between A and H, if you're sufficiently clever, you can probably do it even without Dijkstra's. But we'll go over this, and then the bonus problem is related to this as well. It's a coding implementation of Dijkstra's algorithm. Uh, we'll discuss it further when we get to the bonus problem. Okay, so problem 1.2 it discusses using Prim's algorithm to find a minimum spanning tree. Well, good news, if you've been following along and you've implemented the code in Java, then today we're going to go over both Prim and Kruskal's algorithms to find the spanning trees. And so you can use your program if you recreate these graphs to solve for this problem and this one. Again, it's another minimum spanning tree. Pay careful attention that this one gives you a graphical input, and this one gives you an adjacency matrix. And so if the length is infinite, it's the same as whenever we printed out the incidence matrices in Java or in the Java console, and it was blank. Right? So it just means there's no edge connecting them directly. Okay. Okay. Now trees. So given the following tree and callback function, what would be the output for a pre-order traversal? And so we will probably discuss this, but we'll wait till next time. But I'll let you think about this, because we did spend some time discussing pre-order, in-order, and post-order traversals. And again, in order only applies if it's a binary tree. But we'll come back to this. I'm sure it won't be too difficult. But I don't want to do it today, and I don't know if we'll have time on Thursday. So it might be one of those deadline things where we get it done on next Tuesday before the exam is due. But hopefully we have time for it next week. Okay, so all the same, you should be able to get this, I believe, from the notes, and if not from the notes, then from the book. And so it's asking for output, so it's going to be tag name. It's going to be a list of these string values based on the whatever node is currently being visited. So it's spitting it out in that order. Right? Okay. So use breadth first traversal to generate a tree from the following graph, beginning at node F, and assume that the children are iterated in reverse lexicographic ordering, yada yada yada. Okay, so breadth first just means that that you come back to it. You pause and you come back to it, right? So just one step deep, or I guess two steps deep, you can already see the difference between breadth and depth. Right? So so if we were to generate a tree, and we're iterating in reverse lexicographic order, right? So then we would start down here. right? But if we were starting up here, right, then we would go, and if we were going in normal lexicographic order, and I'll let you think on this a little bit, then in depth first, we would go to A, and then we would visit B, and then from B, we would insist on going until everything is exhausted. So then we would go B, and then D, and so forth. But with breadth first, we pause and we come back. We say, okay, well, we know we need to visit B, so let's mark it. And then we also need to visit C, so let's mark it and come back to it, and so forth. And then once we've finished our wish list from A, then we visit the first one in our queue, and so on and so forth. So that's breadth first. Okay, we might come back to a better example than that, but that's the spirit of it. Okay, and then the bonus problem. So Dijkstra is a shortest path algorithm. I ask you to implement it in C# or Java. Let's see, we will on Thursday do an example of this in JavaScript, so it's kind of just porting it. And then, yeah, I mean, we could take a look at the topics that each of these concerns, so that you're at least refreshed with them. So you should have a fair chance at it, but you're only going to get these two today in all likelihood. If there's time, we'll come back and we'll do this pre-order one. Okay, so great. Now we can get back to coding. So we left off and we had just finished implementing a graph in Java. Oh, this is supposed to be zoomed in, sorry. And then I guess the results should probably be zoomed as well. Okay, well, this is absurd. There we go, that's better. That's fine. Okay, so vertex and edge, you know, still small, but there's not a lot to them. They're not going to change. All of the action that's being added is being added to the graph. So we implemented string display for incidence matrices as well as for adjacency matrices. But now we need something to actually solve the system. So over here we've initialized a graph and we've connected all of the vertices with some prescribed edge weights. And we can see the output of what it looks like in two different ways, the adjacency matrix and the incidence matrix. But really, we want to use it to solve the problem, right? You have two exam questions totaling something like 30 points that depend on our ability to solve this, to create this spanning tree. So with great eagerness, let's dive into it. Okay, so now we want to write a function in the graph class that generates a spanning tree and returns it. And because I'm familiar with it, I know that we are going to end up throwing an exception. But normally you would add this line whenever you come to it, whenever you realize that the method does in fact throw an exception. It's also not helpful to have, you know, right as you create the function, to have it complaining to you that, you know, that something's wrong right out of the gate, when you haven't had a chance to define the function. So we'll come back, we'll add this, you know, later, whenever the time, whenever we figure out where that exception actually occurs. So now we know that we want to return a spanning tree, so we're going to need a spanning tree variable. And remember that we said that a tree is a special type of graph. So we have something that represents a tree, but we don't have a graph. So we'll use this to our advantage. We'll create a new graph, and that will be our spanning tree. And then we give it a new name for one. But as we go, as we build it up, we're going to enforce the requirement that makes a graph into a tree. So it has to be simply connected with unique edges, or with a unique path between any two vertices. So everything has to be accessible through some edge or some series of edges. Like it can't live on an island to itself, right? Like otherwise it's not connected. So everything has to be connected, and then there has to be this unique path from any one vertex to another. So we're going to enforce that as we go, and that will allow us to call our graph a tree. And the way that we do it, it'll be a minimum spanning tree. Okay, so we've defined our return variable, but we're going to need these convenience methods as we go. Sorry, these convenience variables. So we're going to use lookups. We're going to use two lookups. We're going to have one that takes a vertex name and tells us, well, actually, I'm going to have to step back here a second. It takes a vertex name and tells us what root it's associated to, but we haven't really spoken about what the roots are. So let's discuss these separately. So, okay. So how do we grow this spanning tree? We have a graph, and it does. It just exists, right? It has these weighted edges. Okay. Okay, so there's two approaches, and they both give you the same total weight in the tree. The first one says just sort the edges, like ignore the vertices to start, consider every edge, and then just take the next smallest edge. So if we were to sort them, then we would get them in this order, right? Weight 5, 7, 8, and 10. So this one, this one, this one, and this one. Okay. So the first method says just look at the edges, ignore everything else. It doesn't matter. So the smallest edge, the smallest weighted edge, has to be in the spanning tree. So we start by consuming this one, because it's the smallest one. And then it says, okay, just go down the list. Take the next one that doesn't violate the constraint of it being a tree. Okay. So the next one is 7. If we look at this, then it's still, the thing that we're tracking is still a tree. So it's not clear right out of the gate what's supposed to be the root on this tree, but we know that we have a tree. And then that algorithm, so the one that says just take the next smallest edge that doesn't violate the tree constraint, will then tell us to take this one. And at this point we can either stop because we've included every vertex, or we could continue through our list, knowing that our ability to filter out edges that violate the tree constraint, that is, that create some closed circuit, will be thrown out. So if we complete our iteration through the collection, then we'll throw out this one, because A, B, C, and D, or well, in particular because A and C are already a part of our tree. And so if we included another edge, it would either violate simply connected, or it would violate the unique path. So we could get from A to C directly, or we could come around A, B, D, C. So we wouldn't have that uniqueness. And that, again, is what is the defining characteristic of a tree that comes from a graph. Okay, so that's one method. So the other method Okay. The other method also says, okay, start by sorting the edges from least to greatest. Take the minimum edge, the smallest edge, and then grow your tree from there. So now we consider every edge from our tree, from our known tree, that spreads out to something that's one edge away. All the vertices that are not yet in the tree but are one edge away. Okay, so okay, so then the next closest edge from here would be this one, right, 7. And then the next one from there would be 8. So we end up with the exact same tree in this case. And we missed out on some of the more interesting conditions. So what about the case that that everything has more than degree 2? So what if we had right, and they all just get bigger from there. So we end up with something over here, which is the smallest edge, and the next thing is over here. Well, we've identified the 2 smallest edges, and we know that because they don't violate the constraint, that whichever algorithm we want, both of those will end up being pulled in eventually. Prim's algorithm, the one that has to grow from the existing tree, circumvents this by saying, well, you choose, and then eventually it'll end up including the other one. But it'll grow out from that initial seed. But Kruskall's algorithm, which says just take the next smallest one that doesn't violate the constraint, gives you multiple trees right out of the gate here. So you'd end up with one tree over here and one tree over here, and then each hoping to eventually absorb the other one. So as we go along, you're going to see some logic that kind of handles that. So in principle, it's really simple. You just take the next smallest edge, and if you were doing it as a human, you would know, okay, well, this one violates the constraint that we cared about, whatever. But because we're doing it programmatically, we have to be very specific about how we handle, you know, these mergers or whatever. We do have to, if we're going to say that each tree has one root, well, whenever 2 trees merge, which one becomes the root? So that's a condition that we'll have to treat as we go along. So that question, this question, what do you do whenever you have 2 whenever you have the seeds of 2 different trees attempting to grow into the spanning tree, is the reason for all of these lookups and all of this additional logic, when it seems so simple if all you have to do is sort the edges and then pull it in. So yeah, we start there, and then we start excluding, and then we handle the case where we have to merge as well. And that's basically it. So let's get back to it. Okay, so the vertex to root map. Now we want to know that we come along, we get this additional edge. It may already be linked to a tree. It may be the one that connects 2 different trees. It may be one that creates a loop if it's included in one tree or another. But we're sorting by edges, and the edges have 2 vertices attached to them, right, one on either end. And so we need a way of knowing what's going on with the edges that are, or with the vertices that are bookending our edge as we go through it. So these lookups will make more sense as we go. But we want to be able to look it up in either direction. We want to get to take a single vertex and look up the root for whatever tree it's attached to. And then we also want to be able to take a root and then get the list of vertex names that are a part of its tree. And so we'll be maintaining those as we go along, and they'll assist us in defining this. And then the priority queue is going to do the work of sorting these edges for us. We'll just pull the next smallest edge. Okay, and so we give it a size, and then we give it a function, a lambda expression that will perform the comparisons for us. So we've told it that we want it sorted whenever we ask for a priority queue. Now we need to tell it how to sort, like what is the property that it's looking at. Because memory address is arbitrary. That's not a good sorting criteria. So we want to use the weight of the edges as our comparison, our method of comparison. And we're going to use the built-in integer comparison. Because I couldn't remember, I think it's E1 minus E2, right? You return the weight of the first item minus the second item. But you know, if you can't remember, use the built-in functions. Okay. So now, anytime we add an edge to the edge queue, it'll be sorted based on this criteria. And it's a priority queue, so we'll look over heaps or priority queues later, eventually. But for now, we'll just have to recall that it provides some order, some priority. Okay. So next, we want to sort the edges by ascending weight. So the graph itself, the current instance of the graph class that we are operating on in order to generate this new spanning tree instance, has a collection of edges that it maintains. And so we are iterating over that collection in order to populate our edge queue. So that's where we get the edges. It's from the current instance of graph. Okay. Okay, so now we want to actually, this is more for prem. Here, we want to include the next eligible node, or the next eligible edge. Okay. So we know how many vertices we need because that's exactly the total number of vertices in the graph. Otherwise, it's not going to be simply connected. Okay. So now we check to see if there's an edge in our queue. And this condition that we're testing for occurs only if the graph is not connected. So we should run out of vertices before we run out of edges. But if that assumption is violated, then we need to account for it, hence the test. Okay. So remember, like as we're developing, we're going to make a lot of assumptions, and it's important that you develop the habit of testing for these things to indicate what it is exactly that you're assuming to never be the case before you carry on writing your code. Okay, so each edge has a source and a destination. So we're just pulling those, the name of those, because that'll be the string that we use to look them up. It's their ID. And then we want to test, we want to know whether either node has already been claimed by some tree, some other seed, right? And remember that Kruskal is the one that can have competing seeds that are attempting to grow into the entire spanning tree. So we want to know whether or not the source is claimed or the destination is claimed. And because there's going to be two Boolean variables, there's 4 possible outcomes from that. We have the case that that neither one of them belongs to a tree yet, in which case they're going to create a new seed. We have the case that both of them have been claimed, in which case we have to test to make sure that they've been claimed by different trees, in which case we want to merge the trees. Or if it's the same tree, then we want to throw out the edge. So 2 Boolean variables implies true or false squared, right? 2 to the 2, right? So there's 4 flow control branches that come from this. So the first case is 0, 0. So neither the source has already been claimed by some tree seed, some growing tree seed, nor has the destination been claimed, in which case we're going to get a new seed. So unclaimed vertices is no problem. They are always going to be adopted or adopted by an existing tree or create their own tree. If in this special case where neither vertex associated with a given edge has been claimed, then it becomes its own tree. It stands alone. Then we add them to our graph, our spanning tree, which will be our resulting graph. But then we have all sorts of we have a few tracking mechanisms to help us make sure that we are growing the graph and consistent with the requirements of a spanning tree. And so here, because we're growing the graph, we grow it by adding the vertices as they're discovered, and then connecting them. And connecting them creates the edge in the new spanning tree graph. What am I missing here? Oh, okay. And so that was where the exception could have occurred. So now we can finally add that. Oh, and it's because I didn't have the S. Okay. Okay, so it's finally stopped complaining at us. So now we've connected the vertices. So we've added each vertex, and then we've added the edge, or defined the edge that connects them. So now remember, this is our return variable, okay? But we also have these helper lookups, and so we need to make those lookups aware of the state of our our burgeoning tree. And then because we have to choose which one gets to be the root, we'll just say that source is going to be the root. And it's arbitrary. There's no correct root in this case because we haven't given it any condition. So the source vertex name maps to the root of that tree, which by this arbitrary choice is the source vertex. Likewise, the destination vertex will also map to that. And then the other lookup is the one that accepts a root vertex and then says all of the vertices associated to it. So we're saying this new root vertex, which was arbitrarily chosen to be source, is going to have this array list associated to it. And that array list will be populated by all of the known vertex names in that tree, which at the moment is just source and dest. Right? Some new edge, some next smallest edge, or the smallest available edge, with two unknown vertices is discovered. And so in Kruskal, that means that we create the concept of a new tree, seed, or sprout, or just tree if you want to call it that. And then we include both vertices, both of these previously undiscovered vertices, and the edge itself in our copy, which becomes our spanning tree. And then to help us along, we add it to both our lookups, the one that takes a vertex name and then returns the root to the tree of which it is associated, like the tree spud or whatever, the tree sprout. And then in the other direction, the one that takes a tree's root name or a tree sprout's root name and then returns the collection of node names associated to that particular tree. So this will allow us to merge our trees whenever the time comes, and also to make sure that well, yeah, it basically all goes to the merge, and to make sure that we're not creating these closed loops, or these these loops, the ones that violate the tree constraint that we're aspiring to avoid. Okay, so now there's two other cases. One is that the destination is known to the spanning tree, but the source is not. So then we're just adding a vertex and an edge. And again, we don't have to perform any merge operations. Unclaimed vertices walk right in. So we add the vertex and then we connect it, and we already said that the destination vertex was known. So the edge will map from the destination to the source vertex, which the spanning tree just became aware of. Okay, now we need to maintain our lookups. So again, vertex was already associated to some tree sprout. So we need to find out what the root is for that particular tree. So we do that using the vertex to root map. That was the point of that lookup. We give it the destination vertex name. And then we add it to the list of nodes known to that given tree sprout. So we get the list right here that we just created. Right? So the key is the vertex name, and it maps to a list. Right? So we look it up using the vertex name, and then that will return a map. And then to that map, well, it's a list. I should probably call it a list, vertex list, but whatever. It is itself is a map. The route to vertex list is a map. Anyway, so we're getting this list back, and the first time a tree sprout is created, it has two vertices associated to it. It's whatever happened to be attached to the edge that was consumed. So now we're appending to that list, and source is the new one, so we add the source vertex name. And then we update our other list in case we ever have to merge this, which will more often than not be the case. Okay. And then we're going to do the exact same thing in the alternate way, where source is known but destination is not. So again, the unclaimed vertex gets added without question. So whenever we add it, we make the vertex known to the tree, along with the edge that affixed it to our growing tree sprout. Okay, and then again we have to update our lookups, and if you want to speed this up, you can remember that we're doing the exact same thing, but anywhere that we saw destination becomes source, and anything that was source becomes destination. So we get source, destination was unknown, but source was known. So we get the root name for the tree that source associates it to, itself to, and then we get the vertex list from the root to vertex map, passing it the root name, and then we append the destination vertex name, which had been previously unknown to the spanning tree, and then we update our other lookup, vertex to root map. So we say destination vertex name is now associated to root name. So it has adopted that as its root, and the lookup reflects it. So now the final case is where they are both already part of a tree. And so we need to know, what do we do? If the vertices belong to the same tree, then we throw out the edge, we skip it. Otherwise, if they're different trees, we have to merge the vertices into a single rooted tree. So we have to ask our lookup, what is the root for the source vertex? and then we compare. So if they're not the same, then we merge. If they are the same, well, we just ignore it. It goes back to the top of the loop. So are the source root name and the destination root name the same? Hopefully not. Well, I suppose we should be impartial. It doesn't matter. But in the case that it's not, then we connect them. So the spanning tree becomes aware of them, our return variable, our return graph. And again, that's the easy part. But now we have to update our lookups. And again, just like we chose source to be root arbitrarily up here, right? Whenever you have to choose. Again, we have to choose. It doesn't matter which one we choose, but we do have to say which one is going to absorb the other. So we'll choose the convention that source absorbs destination. So we have a list of nodes that are going to be plucked from one tree and moved to the other. And that list comes from the root to vertex map. And because we chose source to eat or absorb destination, the one that's shrinking away is going to be the destination. And the list that is going to grow is going to be its complement. And now we do the actual work of pulling it in. And then this one, so we have the lookup that says what the root is for a given vertex name, and so we're updating it because previously destination root name was the answer to this question, but now for all of the ones that are being absorbed, we have to update that value in this lookup. So again, this is all maintenance work that allows us to construct the tree. But you'll notice that in each of these, most of the work is done in the lookup, in providing the guarantee that our answer, that our response, our spanning tree object, is going to be a tree. And so that can happen. In order to guarantee this, in order to conform our response object into something that satisfies some new quality, there's a lot of overhead, not just in constructing said object, but in guaranteeing the promises made in this condition by having a tree, by claiming it's a tree. Okay, and the maintenance that you have to do is going to end up being specific to the algorithm chosen. Vertex map. And now that one tree has been fully absorbed, it's no longer a root, right? So we remove it from the root to vertex map. Okay. Everything still compiles. Okay, it's satisfied. So now let's test this out before we move any further. Okay, and after that, so we have a method that throws an exception, so we need to wrap it in a try-catch block. But it throws an exception whenever we're instantiating edges. So if we try to connect two vertices where one of the vertices doesn't exist, then an exception is thrown. But because we're basing it off of an instance of a graph object, we're pulling known vertices. That's not possible. So, you know, I'm not sure how other people handle that, but for myself, I note it. Just saying an impossible exception occurred. But treat it like any other. If it turns out to not be impossible, we'll know. But in this case, it is. But still, you want to, anytime you are in a catch block, you would like some awareness that something out of the ordinary happened. Something that breaks the ordinary flow of events. Okay. So we want to get a tree from this object. We've already generated a graph. So now we call in the method we've just defined. Make a note to ourselves what it is that we're printing. And then we'll use the incidence matrix. Okay. Excellent. So we can just go along. Okay, we can just go along edge to edge and add up the weights to find out the total weight. Or we could add a method that prints the total weight of the tree. Either way, but I know that this is the total weight is 23. I'll leave it to you to verify adding those up. So now let's generate it using Prim's algorithm. So Kruskal was the one where we were willing to have multiple tree sprouts that grow, and then one of them will eventually blossom into this full tree that spans the entire every vertex in the original graph. The Prim's algorithm is more like the blob. The blob has to catch you in order to grow by your inclusion, by your addition. So we're going to implement that version of it. Okay. So again, our signature is a public method that's going to return an instance of a graph. And again, this one will throw an exception, but not yet. So we'll deal with that later. We want to mute all the warnings as we're getting started. Okay, so new graph, supposedly. And it'll be the same one as before, but with the suffix _prim. Again, we're going to have a collection of vertices. But this time, instead of it being a lookup, like a vertex to root lookup and so forth, we just need one single collection of vertices, and we'll look them up by their name, by their identifier. And then the edge queue itself. So before, the edge queue only existed to give us that very first edge, to give us the edge of minimum weight. But now, well, actually no, sorry, this one is the one where we're going to use it to get the edge of minimum weight. And before, it was always giving us our next candidate edge. And this is not going to return null, it's going to return the spanning tree. Okay, so again, we've asked for a priority queue. We have to give it an initial size. It's possible to grow it, but we know how big it's gonna be. And then we have to give it a comparator, a comparison method. And so we just pass in a method that says, look, treat these numbers as integers, and get the comparison of the weight of the first edge compare it to the weight of the second edge. And then we start our blob off, our ever-expanding blob tree, with the minimum weight edge. And each time, as we're going through our edges, we really just want to know whether or not a smaller edge has been encountered. And so edge Q will actually be populating that later. But first we just need our minimum edge to define where we start off with our tree. So now we test the trivial condition that there were no edges in the tree. Hence there would have been no minimum edge. So if minimum edge after going through that loop is still null, we have a problem. But rather than throw an exception, we'll just return an empty spanning tree. And that's a design choice, but again, state your assumptions. So going forward, we're going to assume that we have at least one edge. Now, add both vertices on that minimum edge to our tree. So we get the source name. And I probably could have saved some time by creating a method, get source vertex name, so destination vertex name. But I didn't think that far ahead. So you'll find that as you develop that you find all of these real niceties. But as tempting as it is to add every possible convenience you can think of, you can also get lost down that rabbit hole as well, defining all of these convenience methods that you may never end up using. So as a rule, even if it looks helpful, you only add what you need as you need it, and you don't plan for some future convenience, because in general, less code is better. So you want good code, but if you have a lot of dead code lying around, that doesn't qualify as good code. So the principle that follows is YAGNI, Y-A-G-N-I, as in you ain't gonna need it. So don't add methods like I was just wishing for before you actually need it. And we won't add it now because it in the end it isn't really worth the time, even as convenient as it might seem. And then also, even if you're shipping it out for other people to use, if whoever's consuming your library has to learn hundreds of methods and properties, it can bog them down. It's the type of thing that can be tough to read. No one likes reading that documentation. Okay, so spanning tree, connect vertices. Oh, okay. So again, there's the possibility that there's a vertex that we're attempting to connect two vertices where one of the vertices doesn't exist. And so that's the reason that we had the throws exception, and that's what it was complaining about. But we handled that. Okay. So we've made our new spanning tree, our return variable, aware of the vertices that have now been consumed by our growing blob. And then call connect vertices. So we add both vertices and the edge. And then in our lookup table, we say, yeah, we've already got these vertices. Because now, if you encounter an edge where both vertices are claimed, there's no merger necessary. If both vertices are claimed, they're claimed by the same tree because it's growing out as a blob, the ever-expanding tree. So we just have the one lookup this time. That's called vertices. Okay, so now we want to know what edges we should be looking at. Which ones are actually adjacent to or incident with our blob that it can expand and claim its next victim. So we get that list, or we modify it. And we add on whatever new edges we've become aware of. So in this first instance, both vertices are new, and so every edge that they have except the one that connects them is going to be new for consideration. Yeah, so everything except for the edge that connected them, which was minimum edge. So as we go through, we want to add every edge except for the one whose name equals min edge.getName. Okay. And then we want to pull in all of the edges associated to the other end of that minimum edge, the one that is our blob sprout. So again, same logic. As long as there's another edge to consider, I want to keep looping. And then I want to exclude the edge that's already known. Okay. And it's exactly the same. So we could copy and paste that one. Okay, so now we want to grow the tree. And we want to do it using the smallest visible edge. Find the smallest edge, which does not violate the tree constraint. And again, that tree constraint is just that you can't have any loops in a tree. It has to be simply connected and a unique path between any pair of vertices. So there's two conditions. It has to be simply connected and then the unique path. So we know that our final vertex collection has to include all of the vertices in our current graph. And so we have our collection, our queue, our priority queue of, it's somewhere, our edge queue and our priority queue of edges that are incident with our expanding blob. Okay. So we'll pull from that. Okay, and so again, if we run out of edges somehow before we run out of vertices, just break and we'll return however much of a spanning tree we have at that point. Okay, but it won't be what we would consider a solution. We would say that there is no spanning tree. And so you could argue that maybe we should throw in we should test to see if the vertex count matches, and if not, throw an exception rather than return the spanning tree. But you know, for now, that's how we're going to treat it. But again, you know, it's marked. Okay. So now we get our source vertex from this new edge that we're considering. We get our destination vertex. And then we're going to test both of these vertices to see whether or not we're already aware of them, if they've already been added to the new spanning tree. And if they've both been added, then we have to ignore it because only violations of the tree constraint can occur from adding either one. Again means that it would either be multiply connected, so not simply connected, or it would violate the uniqueness. It would create a loop. It would violate the uniqueness of path. So the very first thing we're going to test for is whether or not we are already aware of both of them. Otherwise, we would expect our graph to be aware of at least one of them, since we're growing it out as a blob, as this expanding tree blob. Okay, but if they're already both, if we're already aware of both of them, then we're going to discard the edge because it probably created a circuit. Okay. Otherwise, it means one of them was unknown. And it can't be that both of them were unknown because only that first edge has two unknown vertices, and we took care of that up here. So now we're going back for the rest of the graph. Just like the blob. Okay, sorry. So we add the unknown, or the newly discovered vertex, the one we've just become aware of. And then we connect it to the tree using the edge. So again, we don't copy edges whenever we map it to our new object, to our return object. We redefine it in the image of the original graph. So we're creating a deep copy. There are no objects that exist in both graphs at the same time. It is treated as this immutable object, and so we construct this entirely new object and we return that. So we connect the vertices just as we did when we defined the graph originally over here. Okay. So then we get the weight, and the weight is whatever our current edge is. Okay. So we add the newly added source vertex name to our collection of vertices that have been included in the spanning tree in the return object. And then we queue up all of the adjacent edges, all of the incident edges from that new vertex. Because the blob is already aware of every other edge that it's incident to. So it's only that newest vertex that it needs to consider. And so just like that initial edge, we have to see, well, okay, so we're looking at all of the edges associated with this vertex, but we know that we've just consumed one of them. So we have to exclude that one that we're aware of, as well as any other edges that may lead back to the blob. Those are not productive. So we'll test to see if we need to throw any of those out. Okay, and so edges is again from the collection of the source vertex edges. So if there's a next one, exclude the edge that's already a part of the tree. And if it's not that one that leads back to the blob, then we add it. But I think more properly, we would actually expand this to not just test for that edge, but in the case that we're dealing with a multiply connected graph or a multi-graph, it's possible that we added the minimum edge to join that vertex, and then we have all of these other edges that lead back to the blob. So we could add a condition to root those out, but we test for that over here. So if we encounter an edge in our priority queue where both the source and the destination are contained, then we throw that edge out anyway. So there's really no need to test for it here. It gets filtered out with this continue. Okay. So now we deal with the complementary case where the source was known but the destination was not. And then that actually ends up being the same thing, essentially. So we'll copy and paste that. So again, we add the unknown vertex to our spanning tree. We connect it with the one that's already connected. And we use the same weight as the edge that brought us this new node. And then we add it to our list of known vertices. And then we go in and we pull in all of the edges that are associated with this new vertex, this new node, except for the one that made us aware of it, because we've already included that edge in our spanning tree. So we always throw that one out. And then that's it. Then we have our spanning tree. So now we can go over here and we can test Prim's algorithm. So let's do that. Okay, and try catch. We need to make sure that we have both blocks. I think you can get away without the catch if you have a finally, but that might be language dependent. Again, this exception isn't actually possible. but we have to handle it because the compiler doesn't know that. Okay, so now we create our variable for our spanning tree. And then we print it out. So say what it is we're printing, and then take advantage of our incidence matrix. But we could just as well print the adjacency matrix if we preferred. Okay. So now we run it. We have prim down here. We have Kruskal up here. And if we added them up, we'd see that they were both 23. Okay. How are we doing on time? Hey, not bad. Okay, so that'll do it for today. We'll go back and we'll look over to make sure we've covered all of the other exam material. Yeah, get cracking, you know. So we should cover, I believe, Dijkstra next time, but that won't take the whole class, so we'll get a chance to do some of the other stuff. But all in all, between this class and the next one, you should have everything you need to complete the exam. Okay, well, I will talk to you all on Thursday.